All right. Hi, everyone. Paul here. And I'll actually give you the next three lectures, including this one. So this lecture, I'm going to be talking about deep generative models. And for the next two lectures, next Tuesday and next Thursday, I'll be talking about reinforcement learning and some ways of optimizing for discrete outputs. And then we're going to kind of revisit these deep generative models next Thursday so that we can actually study deep generative models for generating text. So today is mostly going to be on deep generative models for generating continuous outputs. So today we're going to talk about deep generative models, and I think there's a bunch of people doing really good work on deep generative models. I think I'm using some of the material taught at CMU's PGM class and also Stanford's deep generative models class. So today is just going to be a really brief introduction, and if you really want to know more about these deep generative models, you should really look at the PGM class and the deep generative models class for more detail. So let's start. And at any point, just feel free to type in the chat if you have questions, and either me or the other TAs will try to answer these questions as soon as possible. So today we're going to cover three things. We're going to start by introducing these generative models and describe how different they are from your discriminative models, your supervised learning methods that most of you have seen so far. And we're going to start with some basic generative models, and we're also going to go into a class of two very popular generative models. These are called variational autoencoders and generative adversarial networks. We're going to go into some detail. And these are some really powerful generative models because they leverage both the strengths of these graphical models, which give you structure and modeling your data. And at the same time, they also combine it with these flexible and scalable inference that you get when you use like these deep learning and neural networks. So these have been very popular and used a lot in generating images, in generating text, and in generating all sorts of multimodal data. So we're going to go into in-depth explanation of both variational autoencoders and generative adversarial networks. So starting off with generative models. So generative models, usually you're given data, just X. You're not given labels X and Y. So you're just given some text, some images, videos, or some high-dimensional multimodal data. And the goal here is to model P of X. And this is different from discriminative learning or supervised learning. We're given both data X and labels Y, and you try to estimate Y given X. So that'll be estimating the probability of P of Y given X. So in this case, we just want to model P of X. So what does it mean to model? So there's a couple of things that people usually look at when they're trying to both learn and evaluate these generative models. One thing is that if you learn P of X, if you're given a new X, you should be able to evaluate P of X. So realistic looking data, so usually realistic images, should correspond to a high P of X values. And likewise, no, images that are not as realistic should correspond to low P of X values. That is more of the evaluation problem. And evaluation is really important because it also allows us to do things like anomaly detection, where you have like some really useful images that look realistic and you want to assign high densities to it. And for anomalies, you want to estimate low densities for it. So that's more of the evaluation problem. Another thing that people usually look at is the sampling problem. So if I learn a P of X, I want to be able to sample new data X according to P of X. So that means regions of high density of P of X, which correspond to realistic looking images, you want to be able to sample them with higher likelihood. And likewise, low regions of P of X, which correspond to unrealistic images, you don't want to sample them as often. So you want to be able to sample these images and sample these texts and therefore be able to generate new data. And in general, this goes for both generative models and also unsupervised learning. The goal is always to do representation learning where you want to learn useful features, right? So if you're looking at these generative models for dog images, you want to be able to define a generative model that lets you sample new dog images, but at the same time, you want to be able to learn features that tell you that dogs have ears, they have tails, they have this particular shape, and so on and so forth. So throughout, like for both VAEs and GANs, not only are they useful for evaluating and sampling new data points, they're also generally very useful for representation learning. So you can take all these latent variables and eventually use it for some task. So these are the main things that people look at when we talk about generative models. Just to go a bit further, in addition to just sampling P of X unconditionally, people also kind of care about sampling according to some content or category C. So you want to build a model and you want to sample P of X given C. So in this case, C can be a category such as faces, outdoor scenes, from which that you want to generate images of. So this is called conditional generation. And a lot of the methods that we look at in this lecture can also be extended to conditional generation. Another thing which people care about is this thing called style transfer. So instead of just generating images from content, you're given both a content or a stylistic change as well as the initial sentence x1 or initial data point x1. So that could look like we're given all these sentences that start from consistently slow. So that describes both content and style. And style is some stylistic change that you want to go from negative to positive. So the goal here is to be able to retain all the content in the initial sentence and just change it according to the style. So you would change consistently slow to consistently good, consistently fast. And likewise for images, you also want to keep the main content. So these are a row of houses. You want to keep the main content, but just change it according to a new style. So this is a style transfer problem. And many of the models that we look at in this lecture can also be extended to take in both C, stylistic attribute, as well as some input data, which you want to keep the content of. So this is a brief introduction to generative models. So how do we actually, what is like the go-to approach most people use when they actually study these generative models? So a lot of people use latent variable models. And what latent variables means is that you're going to start with images X, and these images are high dimensional, and there's a lot of variation in these images due to things like gender, eye color, hair color, pose, and so on. And unless these images are annotated, these factors of variation, such as gender and eye color and hair color, they're not explicitly available to you. So these are what we call latent variables. So latent variables in general are unobserved variables that you would like to explicitly model so that given another set of latent variables, you can generate more data. So what this looks like in a Bayesian network format is that you would have data X, and if you recall for Bayesian networks, LP went over it last lecture, you always have these nodes, and these shaded nodes represents nodes that are observed. So in this case, your data X is observed. And the nodes that are not shaded are those that are hidden or are latent variables, so they're not observed. And these are essentially the ones that you want to learn. And these directed edges basically model this generation process, in this case, going from Z to X. So you model your conditional distribution P of X given Z. So you only have a data set with these shaded variables X that are observed. You have these unobserved latent variables that you would like to correspond to these high-level features, such as gender, eye color, hair color, and pose. So ideally, if you had a lot of domain knowledge about images, about these face images, and you had lots of data, then you could define a generative model exactly. You could define this latent variable model. So you could have some variables like gender. You could have a hierarchy where ethnicity determines both eye color and hair color, and you would have pose. And together, pose, eye and hair color, and gender would generate your image. This would be ideal. But of course, in the real world, you don't have that much domain knowledge. Sometimes it's really difficult to specify all these conditionals by hand. And they're usually unobserved. So usually you're just given a bunch of images without labels for the people's gender and eye color and hair color that are appearing within these images. So then what we can do is that we can learn these latent variables instead. And that is the whole goal of these generative models or latent variable models, which is how can we learn these unobserved latent variables? How can we learn both their values, the distributions, and their structure, only given observed data points? So we all know that neural networks are very powerful. Neural networks are able to learn many nonlinear functions and approximate many complex distributions. So what we can do is that we can just try to learn these using neural networks. So in this case, X, again, they're images, and we're going to assume Z is some continuous latent representation. And since it's continuous, we can put a prior on it. And these priors, we can just choose a Gaussian prior, which is the most standard prior someone would choose for a continuous representation. So given a prior on Z, how can we define this generation process P of X given Z? as given by this directed arrow. Well, we know that neural networks are powerful. So what we can do is that we can define a Gaussian distribution where the mean and variance are nonlinear, highly complex nonlinear functions of z, as parameterized by mu theta and sigma theta, where theta are your neural network parameters. And by making mu and sigma deep or convolutional or recurrent, you're able to express many types of structures in real-world data. So if you want to model images, you could start with some simple latent representation and have a bunch of convolutional layers to actually generate the image. And likewise, if you want to model text, you can start with, again, a continuous representation Z, and you could have like a sequential autoregressive decoder using recurrent models or transformers to actually model text. So these are really expressive methods. And the hope here is that after training, Z will actually correspond to meaningful factors of variation, these meaningful latent variables. And another good thing that we want is that, given a new image X, we want to be able to encode these features. So we want to be able to do feature extraction, not just generation from Z to X, but also given a new image X, I want to be able to uncover what representation it is so that I can eventually use this representation for a bunch of tasks that I care about. So you might want to model POC given X as well. So obviously, using neural networks, they're powerful, they're great, but they're also very hard to solve, and we'll see some of these issues soon. But let's just start simple. Let's start simple, I think, with a simple generative model that everybody knows, just to kind of motivate what these latent variables are. So hopefully everyone has seen a mixture of Gaussians. In a mixture of Gaussians, there's two sets of parameters. So first of all, you're going to start with the latent variable Z, and this Z basically represents which cluster you're in. And you're going to define a categorical distribution over these clusters. And given this particular cluster Z, each of these clusters are parameterized by a single Gaussian with a single mean and a single variance. So each of these clusters look like this. So blue corresponds to a first cluster with mean mu1. You have another cluster in red, another cluster in green. So although each of these Gaussians are very simple, by having a mixture of Gaussians, you're actually able to cover many modes in data, and you're actually getting a pretty expressive model. So what a generative process is that you want to be able to first sample Z, in this case from a categorical distribution, which defines which cluster you're in, and then you want to be able to generate a data point by sampling from that Gaussian. So if you chose your categorical distribution to be this Gaussian, and then you would use the third mean and the third variance to actually sample data from this third Gaussian. And mixtures of Gaussians are actually pretty useful. Given data, you're actually able to fit these latent Gaussians to cover the space and actually learn these clusters such that they group together semantically meaningful parts of the data. And oftentimes, again, in this case, we have a very complex data likelihood, and that's shown in red. And we are actually able to approximate this data likelihood by just 3 Gaussians. So when we're talking about these generative models, what we usually care about is actually being able to measure P of X, both to sample from it and also be able to evaluate it for new data points X, and sometimes also to optimize it so that you can maximize this log likelihood from data. So we know that Gaussian mixtures are really simple, and we can solve them using expectation maximization. And they're also pretty useful in learning these clusters of data. But one issue with these Gaussian mixtures is that they're unable to learn features. So given a new data point X, you're not able to learn what a good representation of this data point is. Because in some sense, this mixture of Gaussians only defines a generative process that goes from your latent variables Z, your mixture of Gaussians, to data, but it doesn't encode, it doesn't have an encoding process that actually takes data and encodes it into this latent representation Z. So Gaussian mixtures actually motivate. VA is actually an extension of these Gaussian mixtures, where instead of defining these the P of X given Z as these simple Gaussians with like a single mean and a single variance, we're actually trying to learn the means and variances of these Gaussian distributions given some latent representation Z. So how do we actually learn these variational autoencoders? So again, we're going to start with a joint distribution P of X and Z. And we're usually given a data set D, where for each data point, we only observe the X variables. If you recall this Bayesian network, X is the shader variable that you observe, and the Z latent variables are ones that you don't observe. So how can we learn what these Z's and what these parameters should be? So as usual, we're going to do a maximum likelihood estimation. We're going to try to maximize P of X for X across a data set, and we're going to take log because taking log allows us to transform this product into a sum over logs. So this is in general any model that you have with some parameters. You're going to try to learn these parameters data such that they best fit the data. That's maximum likelihood estimation. So now you have this term, your summation of your data points, and you're going to take the log likelihood of each data point. And we know that we have this structure as imposed by this graphical model. So we have both X and Z. So how can we bring Z into the picture? Well, what you can do is you're going to take, instead of just modeling P of X, you're going to model a joint distribution between P of X and Z. And to go from a joint back to your X, you're just going to marginalize by summing over Z. That allows you to incorporate both X and Z into the picture. But what we're going to soon realize is that this summation over Z is highly intractable. So if Z was binary with just 30 dimensions, you have to sum over all 2 to the 30 terms of Z taking on each particular configuration. And if Z is continuous, this integral over all possible values of Z is also very difficult, and you're not going to get a closed form solution. So soon you realize that while you want to use neural networks to learn this variational autoencoders, you're going to run into a lot of troubles, especially when you try to model this high-dimensional data with also high-dimensional latent representation Z. So the key here is that we need cheaper approximations to actually be able to optimize for these VAE parameters. So how are we going to do that? So for the next few slides, I'm going to kind of derive the training process, the approximate training process of variational autoencoder. I think variational autoencoders have been here for a long time, but it's still pretty important to know how these things are derived, because these derivation techniques are useful not just for variational autoencoders, but in general useful for many approximate inference methods in complex graphical models. So here's what we can do. So again, we're going to start with log of your joint. We know that this joint, this summation over Z is very difficult to compute. So instead, what we're going to do is we're going to introduce a Q of Z at the top and Q of Z at the bottom. So these will cancel to 1, so I can just multiply this inside. Why is this useful? So by taking summation over Z weighted by Q of Z, that basically converts to an expectation over Z. Expectation over Z of what? What's left over inside is your joint divided by Q of Z. So why do you want to do this? So intuitively, you want to choose Q of Z, which is what we usually call a proposal distribution. You want Q of Z to be simpler. We know that your joint distribution is complex, your P's are complex, but I'm going to choose Q to be a simpler distribution, and allowing me to a simple distribution that actually allows me to sample Z from Q of Z and compute this expectation using multi-causal samples. So right now we're still not there yet. Usually you want expectation to be right on the outside, right, so that you can actually convert this expectation into an empirical average. But we have a log on the outside. So what can we do? So we're going to use a Jensen's inequality. Jensen's inequality basically states that if you have a concave function, which looks like this, so for concave functions, what it means is that if you just take 2 points and draw a line between them, the value of the function lies above that of the line, right? So log is concave because log essentially looks like this without it dropping down. So Jensen's inequality basically states that if you have a concave function, log of the expectation is at least the expectation of the log. So we're going to apply Jensen's inequality here and change our log of the expectation to be at least an expectation over the log. And this is already starting to look better. Why? Because right now we have an expectation on the outside, and we know that if Q of Z is chosen well, if Q of Z is simple to evaluate, I can actually sample Z from Q of Z, evaluate what's on the inside, and then convert my expectation into an empirical average. And we know that if you take enough samples, if you take enough samples, this empirical average will actually be a very good estimate of the true expectation. So this inequality here is called the evidence lower bound. In particular, this term on the right-hand side is called the evidence lower bound. So again, what we started off was we had this data log likelihood, which is what we care about. This is really difficult to compute. And I was able to introduce this proposal distribution Q of Z that allows me to derive this evidence lower bound, which at least we're starting to get an easier way to compute it. And this evidence lower bound actually holds for any probability distribution Q over your latent variables. So this evidence lower bound, you're going to start with your data log likelihood. It's at least this amount. If you look at this a bit more, it's actually equal to the expectation over Q log of your joint. I'm going to move this log of Q to the outside minus the entropy of Q. So entropy is a term in information theory that quantifies how much randomness there is in this distribution. So intuitively, if Q of Z was uniform over Z, that would have the highest entropy with the most randomness. Gaussian, because it's peaked at its mean, would have lower entropy as compared to a uniform distribution. And what would have least entropy would be something like a delta distribution that is just deterministic at a single point with probability 1. So we know that this evidence lower bound holds for any probability distribution Q over my latent variables. And equality actually holds if Q of Z is exactly equals to P of Z given X, my posterior. And that makes sense, right? For Jensen's inequality, what we essentially did was that if this concave function was exactly equal to the line, then they'll be equal. This would be equality. And similarly, if Q of Z is exactly equal to your P, you will get equality. You will be able to exactly compute your log likelihood of your data using this term. But of course, in practice, we know that P of Z given X is really difficult to compute. And we want to choose Q of Z to be as close to P of Z given X as possible while being easy to compute. So in practice, we can never hope to have equality and optimize the data log likelihood exactly. But instead, we're going to try to choose Q of Z to make the evidence lower bound, which is a lower bound to your data log likelihood. I want to make this lower bound as tight as possible, so that by maximizing this evidence lower bound, I can also approximately maximize my data log likelihood. So I want to choose Q of Z to be as close to P of Z given X as possible while being easy to compute. So this term is quite vague. What does it mean for a distribution Q to be close to a distribution P? And there are actually methods in statistics that allows us to quantify how close two distributions are to each other. And one thing that is most useful here is this KL divergence. This KL divergence is exactly one type of divergence in a class of many divergences that allows you to estimate the divergence between two distributions. So the KL divergence is given as follows. So the KL divergence between Q and P is given by an expectation over Q, log of Q over P. So this integral over Q, dz is exactly the expectation over Q. And this term inside will be log of Q over P. So first notice that this KL divergence is not symmetric. The KL between Q and P is not the same as the KL between P and Q. So then you might ask, why do we want the KL between Q and P and not the KL between P and Q? Well, again, it goes back to the fact that if you have a KL between Q and P, you can compute it as an expectation over Q and something here. And the expectation over Q is something that we can actually approximate if Q is simple enough by taking samples from Q and taking the empirical average. If I had the KL between P and Q instead, then I'll be taking an expectation over P instead. And P is what we started off with. P is a really difficult data log likelihood function that we do not know how to compute. So by taking KL between Q and P, we are actually able to choose Q to be simple and therefore be able to compute the expectation over Q more realistically. So we look closer at this KL divergence, just because it's an expectation over Q. Let's take a look at what sorts of cases will make this KL large and what sorts will make it small. So we know there's an expectation over Q. So if Q is small, then this first term is going to be low. you're going to be weighting it by a small value of q. And that means you don't really care what the term behind it is. Just because q is linear, is a linear term, and log of this is going to be a logarithmic term. So as this is small, it doesn't really matter what this is. It's going to be dominated by this small q of z term. So if q is low, then we don't care. So we really care about the cases where q is high. We're taking expectations over regions where q is high. So if q is high, then this is going to be high. And basically, I want to learn. I need this p to be high as well, so that this term is close to 1, and log of 1 is going to be 0. So that would incur a small loss to my KL. On the other hand, if q is high and p is low, we're going to take a large value divided by a really small value. This is going to be huge. And that's when you pay a price. If q is high and p is low, that's when we have to pay a price and incur a large amount of cost in KL. So what it looks like pictorially is, if I have p, again, p is a really complex distribution. It's defined by your data. It might have multiple modes corresponding to high-dimensional images. You can't compute what p is. You're going to define a simpler distribution q. If q is low, so in these regions, q is low, we don't care what p is. And for regions where q is high, I want to make sure that q matches p almost exactly. That's when you can minimize and get a small KL. So note that for this KL divergence to be defined, as you can see in here, like the support which is the values of z over which q and p are defined, the support is really important. And in this case, just because p is on the denominator, wherever q is bigger than 0, it must also be that p is at least 0. Otherwise, you'll be dividing by 0 here. So what a KL would encourage you to do is that, for a very complex multimodal distribution p, I'm going to try to find a q values covers some high areas of p, and it might miss other areas of high p. So that's the KL divergence. So this KL divergence is actually really important in the evidence lower bound, because you can actually rearrange this KL divergence and actually obtain the evidence lower bound exactly, plus the log likelihood of the data. And there's no coincidence here. There's no coincidence why I chose to introduce a KL divergence as a distance between distributions, because that's exactly the term that will appear in deriving these evidence lower bounds. So KL is exactly equal to the evidence lower bound plus the log likelihood of the data. And another property of KL divergence, because it's a distance, that the property is that it's non-negative. So rearranging, we can actually rederive the evidence lower bound just starting from the KL divergence as well. So the log likelihood of the data is again at most, it is at least the expectation over q, log of your joint, plus the entropy of q. And again, equality holds if q equals to p, because the KL between q and p, if q and p are exactly the same, is equal to 0. So the KL is going to be equal to 0 instead of at least 0, which means that the log likelihood of the data is exactly equals to the expectation over q, log of your joint, plus your entropy. And that's not just the best part. The best part is that this KL divergence now exactly gives us a gap. Exactly tells us the gap between this evidence lower bound and the log likelihood of your data. And that allows us to exactly quantify how well our chosen Q distribution is. So the closer our chosen Q is to P, as measured by the KL, the closer our evidence lower bound is to the true likelihood. And again, that reinforces the fact that we want to choose a Q that is as close as P as possible, while making sure that Q is simple enough to sample from, so that you can eventually compute all these expectations over Q. And that is essentially the basis of variational inference. You're starting with this very complex distribution, P of Z given X as your posterior, and you might have multiple modes, and that's shown in blue. And you're going to define these tractable variational distributions Q of Z with some parameters phi. These are your variational parameters. And you want to try to learn these variational parameters such that Q of Z fits this P of Z given X as best as possible. So in this case, let's just assume that P of Z given X is this complex multimodal distribution. You can't even write a closed form for it. You obviously can't sample from it. You can't really compute anything. But what you can do is you can define these variational distributions Q just as simple Gaussians. Simple Gaussians with a parameter for its mean and a parameter for its variance. So in orange here is a Gaussian with parameters mean 2, variance 2, and another Gaussian here with mean -4 and variance 0.75. And the whole goal of variational inference is that you want to optimize these variational parameters phi, so that your Q of z is as close as possible to your P of z given x, while being simple to compute. So in this case, this posterior, your P is better approximated by this orange Gaussian, this orange variational distribution than the green one. So there's going to be a smaller KL between this Q and this P as compared to this Q and this P. That is the whole basis of variational inference. So now we've turned it into an optimization problem, where phi is all possible settings of your variational parameters, and for each particular setting of your variational parameters phi, that's going to define your evidence lower bound in red. At the same time, it's also going to define a KL divergence between Q of z as given by your variational parameters and your actual posterior, which is hard to compute. And with respect to phi, the log likelihood of your data is actually constant. So log likelihood of your data depends on theta, but with respect to phi is actually constant. So the goal here is to find a good setting of these variational parameters phi, such that the KL divergence between your proposal distribution Q and P is as low as possible, and therefore your evidence lower bound is as tight as possible, is as tight of a lower bound as possible with respect to your data log likelihood. If it's as tight as possible, that means that optimizing this evidence lower bound will give you the best approximation to actually optimizing this data log likelihood. So that is the most important relationship here to derive variational autoencoders, which is that the log likelihood of the data is equal to the evidence lower bound plus the KL between your variational distribution, which is free for you to choose, and the true posterior of the data, which is complex, which you want to approximate. So in practice, you want to be able to learn these variational parameters, as well as the other parameters in your model, including theta and any other parameters in your model jointly. So how can you do that? So we're gonna again go to the evidence lower bound. It's something that we derived. We know that this is easier to compute as compared to the true log likelihood of the data. I'm gonna rewrite this evidence lower bound this way. So again, expectation over Q, log of your joint. And we used to have an entropy term, but the entropy is exactly equal to the expectation over Q log Q. That's the definition of entropy. I'm going to subtract log of P of Z, and I'm going to add log of P of Z. So recall what Z is. If you recall what P of Z is, so Z is your latent variables that you want to learn in your autoencoder, and P of Z is just some prior that you're putting on top of these latent variables. So in the case where Z is continuous, you would just put like a Gaussian prior over your Z's. So I'm going to subtract log P of Z, I'm going to add log P of Z. I'm going to group the first two terms together. So this joint minus log of the marginal is going to get log of P of X given Z. And the second term, my log P of Z minus log Q of Z under the expectation of Q is exactly the KL divergence between your Q of Z and P of Z. So let's look at these two terms more in depth. So the first term is actually a reconstruction term. Why is that? So what this term does is that, let's first look at each of these terms in more detail. So P of X given Z essentially takes in Z, and I'm going to define some parameters theta. In practice, these are neural network parameters theta. And I'm going to transform Z into your data X. This is your generator, the generative model. In autoencoders, that's also kind of known as a decoder that takes Z and actually generates your data X. My Q of Z given X will take in X and use parameters phi to reconstruct, to actually predict which latent variables correspond to that particular data point. So that is the inference model, or also known as the encoder model in these autoencoders. So what this term looks at in total is that you're going to first take x, you're going to encode it using your inference model, and you're going to do it multiple times so that we can approximate this expectation. And once you have these latent variable z, I'm going to put it through my generative model and try to reconstruct my data x. That is this term. And I want to make sure the reconstruction of my data x is as high as possible with respect to log likelihood. So that is exactly reconstruction. It encourages the predicted values of x to be as similar to as the input values of x as possible. And the second term is actually a prior. So again, this Q function will take in your data x and encode it into a set of latent variables. I want to make sure that the set of latent variables that I'm encoding using my data is as close as possible to my prior over z. And my prior over z is this Gaussian distribution. So it encourages this set of predicted latent variables through the inference model to be as close as possible to the prior. So all these derivations allow us to get the elbow, which you know that is a good approximation for the true data likelihood. And this elbow can actually be decomposed to a reconstruction term through an autoencoder. So first, inferring the latent variables from x and generating data from x and making sure that x is of high log likelihood, as well as a prior term, which makes sure that given a bunch of samples, x, the latent variables that you encode follow a similar distribution to this prior that you want these latent variables to follow. So that's exactly the autoencoder perspective. This is usually what people just present if they wanted to explain to you variational autoencoders really quickly. But all we did in the last 30 minutes was basically a derivation of why variational autoencoders exhibit a reconstruction loss and this prior loss. So now we know that we have this reconstruction loss and this prior loss that allows us to learn these variational autoencoders. But in practice, because we want to do gradient-based learning and combine it with neural networks, there's actually a trick here. It's not as trivial as it seems to just directly optimize this. So why is that? So we need to compute two sets of gradients. Again, we have two sets of parameters. One is theta, one is phi. So we call here theta is the parameters for the generative model from latent representations to your data, and phi is the inference model from x to your latent variables. So there's two sets of parameters they want to optimize, both theta and phi. So to do that, we want to be able to take gradients of this loss function with respect to theta and phi. So the gradients with respect to theta is easy. Why is that? I can just write it out. A lot of the losses here is the expectation on the Q, log of P of x given Z minus the KL. The KL term does not depend on theta, it only depends on phi, so that goes away. And this term in front here, this expectation is with respect to phi. Again, that doesn't depend on theta, so I can move my theta into the expectation. And this P of x given Z, which is the decoder part of the model that takes Z and outputs x, that is the part that actually depends on theta. So what I can do is that I can replace my expectation over my Qs with just samples from it. So I'm going to take n samples. I'm going to take n samples of these latent variables Z, because this is what latent variable Z with respect to the distribution of your Qs, with the distribution of your latent variables as given by Qs. And for each of these latent variables Z, I'm going to try to use it to predict my data X with using my parameters data. And then I'm going to try to maximize the log likelihood of being able to reconstruct data from these latent variables that came from distribution corresponding to Q. So I can change this expectation over Q using a sample average. So this is easy. Difficult part comes here, where you want to take expectations with respect to phi. So what happens here is that we know that this evidence lower bound actually contains expectations with respect to phi. So you can no longer push the gradient with respect to phi through the expectation and take samples from it, just because this expectation also depends on phi. So what are we going to do here? We're going to use this thing called the reparameterization trick, which is a very common trick. It's very important in these generative models. in this simple setting, again, you want to compute a gradient with respect to phi of some expectation over q, which depends on phi, and some value r. So you don't really care about what value this is on the inside. So this is equal to an integral over z, the probability, the q of z, which is the probability of z that depends on phi, and the value of r evaluated as z, where z is some continuous variable. So what can we do? So let's just assume, because in our settings, our q of z are just Gaussians. Assume that z is an even simpler Gaussian, a Gaussian with just a mean parameter and a variance parameter. So this Gaussian doesn't even actually depend on your input x. So it's just a fixed, or just two sets of parameters, a mean and a variance. So how can we actually sample z from this q of z so that we can approximate this expectation? So one way of sampling is to just directly define this Gaussian with mean and this variance sigma square and sample this entire vector z. Another way of doing so is to just sample a single noise vector, so epsilon from a standard Gaussian. And once you have an epsilon from standard Gaussian, you can actually put this epsilon through a linear transformation by multiplying it with sigma and adding mu. And that actually gives you z with the exact same distribution that you want, just because you have the property of linearity of Gaussians. So that is also an equivalent way of sampling z that also allows you to sample z according to this distribution. But instead, you're not sampling z directly, you're just sampling epsilon from a standard Gaussian. So I'm going to call this linear transformation g. It depends on epsilon and also phi, because in this case, phi is this mean and sigma parameter. So this way of sampling and reparameterizing is actually the key that will allow us to compute these expectations. So normally you have an expectation that requires you to sample z from q of z times r of x. Instead of sampling z directly, I'm going to replace it with sampling these standard unit Gaussians from standard normals. And once I sample an epsilon, I'm going to apply this epsilon through my linear transformation to actually get the z vector, which is from the same distribution that I want. And then I'm going to put this z through whatever r of z that I care about. And what that looks like is that will look like an integral over p of epsilon, because it's sampling these epsilons. And once you have an epsilon, you're going to run it through this linear transformation and actually apply r and the z that you get from putting it through this linear transformation. So what's the benefit of that? The benefit there is that if you now want to take an expectation with respect to phi, you're going to convert it to an expectation over epsilon, your function inside. And now this expectation over epsilon no longer depends on phi. So you can move your gradient with respect to phi into the expectation. And it's only this thing inside the expectation, the function r and g, that depend on phi. So this term is not really easy to estimate by a Monte Carlo. There's a couple of things that you need. First of all, you need epsilon to be easy to sample from. And in our case, epsilon is really easy. Epsilon is just standard normal. You can sample from that very easily. You also need your r and g functions to be differentiable with respect to phi. And we also have that. So in this case, your phi is just, your g is actually just a linear function with respect to your mean and sigma. So that's differentiable with respect to your parameters. And your r function, you also have to assume that whatever operation you do with z on top of it is also differentiable with respect to your parameters phi. And we have that as well, because we're working with these differentiable neural networks, and all these linear transformations and activation functions are differentiable with respect to these variational parameters. So then what you will get is that you will just sample noise multiple times from standard normal. Whenever you sample a noise, I'm going to put it through the transformation defined by these variational parameters, essentially multiply it by sigma at the mean to get the z. And then I'm going to put z through the function that I care about. That's going to give me a bunch of samples. I can now take the gradients with respect to phi because it's differentiable, and I can take an average across as many of these k samples as I want to approximate my expectation. So in our case, we can do that as well. So again, we have this evidence lower bound, which is equal to an expectation over q log of p of x given z minus the KL. We're going to just look at the first term for now. The KL is going to be basically the same. So again, we're going to change the expectation with respect to q of phi to an expectation over epsilon. And whenever I sample this epsilon vector, I'm going to transform it by multiplying it by sigma and adding mu to it to actually get my z vector. And now because of this expectation over epsilon that does not depend on phi, I can move my gradient with respect to phi inside the expectation. So again, expectation over my standard Gaussian samples, a gradient with respect to phi, and a log of my p of x given z. And therefore, you can also approximate this using multiple samples of noise, computing this inner term and computing an average over that. So visually, what that looks like is that you started with x, you're trying to encode x into z using your q of z given x. To encode x to z, you also need your variational parameters phi. A naive method would be to encode, if we learn this distribution q of z given x and phi, and then once you learn this distribution, sample entire vector z. So z is actually a random node. And once you sample a vector z, you're going to go on to your subsequent functions, essentially going from latent variables back to your input. But then you will not be able to backpropagate your loss here over to your variational parameters, because you have a random node stuck in the middle, which creates a bottleneck, because you can't really backpropagate through like a random sample. So what reparameterization does instead is that it just samples a single epsilon. So this is where your randomness is. With this single sample epsilon, you're going to transform it according to your variational parameters to get z. And then you go also put x. So this is your encoding function basically takes in x. It learns your mean and variance using your parameters phi. And then you're going to transform your random vector z epsilon according to this mean and variance to actually get z. So now z is the deterministic function with respect to your variational parameters that gave you your mean and your variance. So now that z is a deterministic vector, you can use that to decode your image and define your loss function. And you're able to backpropagate your loss function with respect to z, which is now deterministic, and also with respect to your variational parameters, which actually produced this mean and variance in the first place. So that is the reparameterization trick. So, so just to summarize, we started with this log likelihood of the data. We saw that was not really tractable, and we derived this evidence lower bound, which is a lower bound to the actual true log likelihood of the data. And how good this lower bound was depends on this variational distribution that you chose, right? You want this variational distribution to be simple. In practice, they're usually Gaussians with mean and variance predicted by your input data. So they're simple, they're easy to sample from. But in practice, because we're actually learning this mean and variance through your neural networks, they're actually very expressive, and they can also approximate your posteriors. And deriving this evidence lower bound allows you to optimize for two things. The first thing being this reconstruction objective, and the second thing being your prior objective. So in overall, how we actually learn a variational autoencoder, you will first take a data point xi, that's your input image. I'm going to define an encoder parameters, so a q of phi z given xi with parameters phi, and that allows you to take in, feed it xi and actually output a mean and variance that parameterizes q of z. So q of z is going to be a Gaussian with mean and variance parameters predicted by a neural network that takes in x through parameters phi. Once you have this mean and variance parameter, I'm going to first sample noise, epsilon from the standard normal, and then I'm going to compute the actual latent variable by a linear transformation of this standard normal multiplied by sigma plus mu. That's a reparameterization trick, which allows us to further get gradients with respect to mu and sigma, and only leave the randomness at epsilon. That allows us to get my actual latent vector z hat, and then I'm going to put z hat through a decoder with parameters theta to actually get the output, the predicted output. And there's two losses. One is a reconstruction-based loss between the reconstructed image and the original image, x hat and your x. And another loss is this KL term between your distribution of latent variables that you predicted using your encoder, that's Q of phi z given x, and the actual prior which you want these latent variables to have, which is your P of z. So yes, so that is a full derivation of variational autoencoders going through variational inference. Again, most textbooks or most lectures will just directly give the autoencoder perspective, talk about the reconstruction of the prior, but many of the techniques here involving variational inference and KL divergence, they're useful in many other scenarios as well, beyond variational autoencoders. Cool. So now that we know what variational autoencoders are, we can talk about some of the applications of variational autoencoders, especially in these multimodal settings, which we all care about. So I think one thing, at least in the unimodal setting, just to begin with that, one thing which variational autoencoders are really useful for is learning disentangled representations. So what disentangled representations are is that you have all these images, and each of all these videos, and all these videos have very specific factors of variation. So in this case, only the floor is changing color. In this case, the background is changing color. Here, the circle is changing color. Here, the size of the circle is changing, increasing, decreasing. So ideally, you want to learn a generative model that not only generates these images, but it can actually generate these images with respect to these disentangled factors. So you want to be able to learn these factor representations, one of them corresponding to the color of the ground, one of them corresponding to the color of the background, one of them corresponding to the color of the circle, so that you can actually change and interpret these different factors that your variational autoencoder has learned. Another motivation for disentangled representation learning is that for style transfer. So again, in style transfer, recall that you're given a particular image with some content and some initial style, and your goal is to keep the content as much as possible. So in this case, the content of houses, you want to make sure you're still generating images of houses, but you're only changing the style of it. So essentially, many of these generative models for style transfer, these representations are disentangled into content variables and style variables. And then you can just manipulate the style while keeping content the same. And that goes for text as well. So how can we actually do disentanglement using variational autoencoders? You can actually do it very easily. So again, you have this variational autoencoders. Once you derive the evidence lower bound, you have this reconstruction objective, and you have this KL term that imposes the set of latent variables you learn to be as close to the prior as possible. So with suitable choices of the prior and suitable learning of this KL objective, you can actually learn these latent variables. You can actually learn this distribution of your latent variables Z to follow this prior. So usually what people do is that we can put a P of Z as standard Gaussian and isotropic Gaussian, which essentially means that across different dimensions of Z, there are no correlations. And if you impose this prior strong enough, what you're actually able to learn is a set of latent variables that are all independent from each other. So in this case, you want to learn one latent variable that's representing shape, independent from another latent variable that represents angle, which is independent from another latent variable that represents scale. So this autoencoders naturally, they actually already learn disentanglement just because you're imposing a prior which is disentangled. In practice, people have found that this set of beta VAEs, essentially having a tunable parameter beta in front of the KL, is easier for disentanglement. So if beta equals to 1, that actually covers your standard variational autoencoders, the evidence lower bound. For larger values of beta larger than 1, you're actually tuning the contribution of your reconstruction and your prior. And larger betas imposes a stronger constraint on the latent variables to have independent dimensions. So this is a very simple way of achieving disentanglement using variational autoencoders, which itself is a very difficult problem. We've seen both positive results for both text and images, but at the same time, there's a bunch of negative results, and also a call for better benchmarks and metrics to measure disentanglement. So feel free to look at all of these papers if you want to know better methods beyond this beta VAE, and also better metrics to measure disentanglement. So one application of disentanglement is actually that for multimodal data. So this is a paper from our group, and the goal here is to apply these variational autoencoders for multimodal data with careful design of these latent variables. So in these settings, we're looking at these data with three modalities. So people speaking in front of the camera, with text, with gestures, hand gestures, facial gestures, and also tone of voice. And the idea here is that I want to learn two sets of factors. So one set of factor is a joint multimodal factor, and this joint multimodal factor, I wanted to capture high-level information across multiple modalities that correspond to things like sentiment and emotions. So things like sentiment and emotions are manifested in text, in visual, and also audio, and they're also used to predict the label. So that's the goal of this multimodal joint factor. And at the same time, I also want to capture these modality-specific factors within each modality. So a language-specific factor should model variations within language, different ways of saying the same sentence with the same emotion. And it also captures how different people say the same things with similar intents. So that would model things like this movie is great versus that movie was awesome. So the goal here is also to learn these disentangled factors, a joint factor, as well as these specific factors for each modality. So we can do that using a variational autoencoder. We can again define a generative network that takes in these latent variables and actually generates your data, as well as an inference network that takes in your data and actually predicts these latent variables. This is also called the decoder that decodes from your latent variables to your data, your encoder, which encodes data to your latent variables. So what this graph here is showing is basically you have a joint multimodal factor, that's your Z of Y, and this multimodal factor is in charge of predicting the labels. Right? You wanted to capture this shared information across modalities that are useful for predicting the labels. So it should be able to generate the labels. And at the same time, this joint factor, which contains label information, should also be able to generate your data. Right? You want your factor representing your positive sentiment to actually affect the generation of data from each modality to actually exhibit positive sentiment. And these modality-specific factors, for language, visual, and audio, they will not generate the label, but instead they will just model variations within each modality. So you're just generating within each modality. So that would model things like your language is going to be positive, but still there's many different ways of saying positive text, and that depends from person to person. So that's what these language-specific factors will try to model. And by using an autoencoder framework, again, you're going to end up with a similar set of losses, a reconstruction loss. So in this case, you're going to sum over each modality, the reconstruction within each modality. And this reconstruction is based on a set of two factors. Right? To reconstruct my language data, you will take in my language-specific factors, and you also take in this joint multimodal factor that tells you language is in general positive. So you're going to do this reconstruction of data within each modality across all three modalities. You're also going to have a prediction loss that estimates how well you're able to predict your labels from your latent variable representing this joint multimodal factor. And you're going to put also all these four factors together and stack them up. And you're going to impose a KL. You're going to try to minimize the KL between these latent variables as predicted by your model with a prior, which is a standard Gaussian, to ensure that these latent variables have no correlations between them and are therefore disentangled. So by learning all these three losses, we're actually able to get really good performance using the discriminative factor. So you get much better performance than the baselines. But more interestingly, you're also able to do generation, which is one thing that your purely supervised learning discriminative methods are not able to do. So in this case, it's really hard to generate these high-dimensional faces and text and audio, but we use a simple example where one modality are these street view house numbers from 0 to 9, different ways of writing these 0 to 9 house numbers, and another one is endless, which is also 0 to 9, these handwritten digits. So you want to learn these, again, you want to define a generative model, where Z of Y is this joint multimodal factor that represents the label being 9. And for each of these modality-specific factors, you will have one of them representing the style of SVHN and another one representing the style of MNIST. So learning such a disentangled representation actually allows us to change each of these factors and generate my data. So if I just fix ZA1, so I want to keep the style of SVHN the same, I can change my label and actually get the same digit in the same style but across different labels, 0 through 9. And likewise, if I fix my my style factor for MNIST, I'm going to get the exact same style, but by changing my multimodal factor, I'm going to be able to generate different digits, 0 through 9, according to the same style. And likewise, if you fix this multimodal factor, which means that I wanted to keep it at the same digit, I want to keep it at digit 5, I can change my SVHN style and I can change my MNIST style independently to get different stylistic variations of the digit 5 in SVHN style and MNIST style. So that is a benefit of actually disentangling these factors so that you can do controllable generation with respect to each factor for these multimodal datasets. And another benefit of these generative models, which discriminative models do not have, is you're actually able to separate these factors, and you're going to be able to, you can measure the gradients with respect to the gradients with respect to the generation of each output, and therefore use that to interpret your data. So what I'm doing here is that the model is going to incur some loss in generating X1, my language modality, and I'm going to measure the gradient of that loss with respect to my latent variables, my joint multimodal factors. And what that essentially means is that it measures the contribution of this joint multimodal factor, which in our case represents things like sentiment and emotions, the contribution of that sentiment factor to the generation of each modality's data. So we're actually able to find that these gradients are actually quite informative in picking up these signals. So in this case, very profound and deep. That represents probably positive sentiment. And the gradient of the generation of those particular time steps with respect to my multimodal factor that represents positive sentiment was actually pretty high. Cool. So just one last application, another really cool application of VAEs for multimodal data. And this is quite different because it actually goes beyond reconstruction. Right? We looked at VAEs, we saw that they all have a reconstruction objective and also a prior objective, but this method actually goes beyond reconstruction, and they also found it to work pretty well. And why did it go beyond reconstruction? Well, in some cases, you don't care about reconstructing, and sometimes it might be also really difficult to reconstruct the high-dimensional input modalities, right? So if I want to learn a variational auto-encoder to learn representations of video data, like reconstructing the entire video might be something difficult. So in this setting, what they were doing is, this was more for robotics. So it was the goal of trying to use a robot hand to complete some task. So this robot would have access to an RGB image of the position of the task. It will also have force data as measured by the robot touching the task and measuring the force exerted on the table. And also have some internal state of the robot that is constantly being updated. So you have all these modalities coming in. You want to learn an encoder that gets you a multimodal representation. And normally, if you just had a variational autoencoder, you would just have a decoder back to the exact same data. You try to reconstruct these high-dimensional images. You will try to reconstruct these long-term time series representing your force. You try to reconstruct these robot state, which can be these discrete factors. And that is in general quite difficult. So what they did was to combine VAEs with self-supervised learning. Instead of reconstructing itself, reconstruct some other signal which you know will be informative for your prediction. And these signals, if you choose them well, they can be much lower dimensional, but at the same time as informative or even more informative as compared to reconstructing the input. So what they did here was that they took this representation and decoded it into three things. One of this was optical flow, which another one was whether a contact was made in the next time step. So that's a binary 0-1 variable. And another 0-1 variable which asks whether my force and my RGB image was aligned. Essentially, these are self-supervised signals that by domain knowledge you can actually define to be important for these tasks. So instead of reconstruction, they're actually learning encoder decoder that actually predicts these things. And at the same time, they're also going to impose a Gaussian prior on these latent representations. So what they found that firstly was these multiple modalities are pretty important. You want to be able to use both force and image to be able to complete your task. And at the same time, by having these multiple modalities, you're more robust to occlusions or imperfect data within a single modality. So you're using both force and vision. So you have external force, you're messing up your force sensor, you can also rely on vision. And likewise, if you have occlusions in visual, like these occlusions from a book, you can still rely on force to still complete your task. Cool. So that's it for variational autoencoders. We saw a brief introduction. We kind of derived the inference and training procedure and optimization of variational autoencoders. And we found that, well, in general, these variational autoencoders are easy to train, and they have an inference network, which means that for a new data point X, you can actually encode it into a latent representation that is useful for many tasks. For cases of multimodal data, we saw that these latent representations learned by variational autoencoders were also useful for discriminative tasks and also useful for like robotics tasks. One issue, though, is that variational autoencoders still rely on reconstruction. Right? We saw that also reconstruction term. In practice, people use mean squared error or cross entropy. They're trying to predict discrete outputs. And that still leads to blurry images. In general, estimating mean square error in high dimensions is not very informative. So if you look at these empirical studies, given particular image, variational autoencoders tend to generate pretty blurry images. But this new set of models that we're going to look at, called Generative Adversarial Networks, GANs, actually generate much sharper images. So part 3, actually going into GANs. And I know LP talked briefly about GANs last Thursday, so I'm also going to go through just a really quick review and also more in-depth parts of GANs. So GANs were motivated by, again, the difficulty in evaluating and optimizing your P of X in high dimensions. Right? We saw that Gaussian mixture models, you could compute P of X exactly. For variational autoencoders, we could not compute P of X exactly, but what you could do was you could compute an evidence lower bound that approximates your P of X and therefore optimizes evidence lower bound. But GANs, what they do is that they just get rid of optimizing for P of X completely. Just because it's really hard to optimize, and even high P of X, as learned by the model, might not really correspond to realistic samples that your model is not predicting. So instead of optimizing for P of X, what GANs do is ask this really simple question. So let's say I have some samples of images that I know came from distribution P. I don't know what P is. I don't want to model P. I just know that it came from the distribution P. And I also have a bunch of samples of images from some other distribution which I know came from Q. So just based on these samples, without estimating P and Q, how can I tell whether it came from the same distribution, whether P and Q are the same distribution or not? And this has a lot of statistical theory, and a lot of these things work in low dimensions. But essentially, a lot of the theory behind this works through these things called two-sample tests. So given a bunch of samples from P and a bunch of samples from Q, the null hypothesis is that P and Q are the same distribution, and the alternate hypothesis is that P and Q are different distributions. So what you want to do is you want to define the test statistic to actually compare how different S1 and S2 are. And the very simple test statistic is just the mean. I'm going to compute the mean of all my samples in S1. I'm going to compute the mean of all my samples in S2. And I'm going to compute the difference in means. And if this difference is less than a threshold, I'm going to say, the means look pretty much the same. I'm going to guess that P and Q are the same distribution. So I'm going to accept my null hypothesis. And if the means are really different, then I'm going to think, the means are so different, P and Q are likely different distributions. So I'm going to accept this alternate hypothesis. So methods like this are good because they're likelihood free. You don't actually involve the densities P and Q. You don't bother learning it. You just rely on samples. And GANs basically extend this where you want to train a generative model. So you have a distribution of your images from your data distribution, and you want to train a generative model to actually get P of theta, to actually sample more images. So give us some real images from the data distribution and give us some images generated by your model. I want to train my generative model to minimize this two-sample test objective. I want to train a generative model to make it seem like my data distribution and my model distribution is as close as possible. And these test statistics are really hard in high dimensions. Again, estimating means and variances in high dimensions are super hard. So what I can do instead is I can learn a statistic using a discriminator. So what I want this learned statistic to be is that the statistic should maximize the distance between S1 and S2 because I know they came from different distributions. And conversely, my generator should try to minimize the distance between my samples S1 and S2 because I want to make sure they look as similar as possible. So that in itself is our GANs. So it's a two-player game between a generator and discriminator. A generator will generate data from Z to X that tries to minimize the two-sample test objective. You want to make it seem like data and your model distribution are as close as possible. And a discriminator would be a classifier, a neural network that tries to distinguish real samples from the fake samples generated by the model. In other words, you want to maximize the objective and want to make it seem like the data to distinguish the true data from your data distribution and the generated images from your model distribution. So you can train these. Jointly. You can define this joint objective that for X from your real data, I want to maximize log d of X, and for X being from your fake data, I want to maximize log of 1 minus d of X. That's basically this binary classification loss. I want to minimize. I want to take true samples and predict them with label 1, and take fake samples and predict them with label 0. And if you really train this to completion, the optimal discriminator is going to take in a point X and actually evaluate the probability under your data distribution and see how close that is. So if it's really close if it's really high under my data distribution, this will tend to 1. And if it's really low under my data distribution, this will tend to 0. And that will correspond to a fake sample. So that's the discriminator. How would you train a generator? Well, the generator is basically the converse of that. Maximizing a discriminator, you will conversely minimize the generator. And the generator will try to basically fool the discriminator so that you cannot distinguish between the true and false samples. So you're going to want it to do badly at this binary classification task of assigning true samples to 1 and fake samples to 0. And if you do some math, you can actually find that if you retrain a discriminator, the objective function for the generator eventually boils down to this term, 2 times the Jensen-Shannon divergence between data and generators, data distribution, and your model distribution minus log 4. So why is this important? So this Jensen-Shannon divergence is actually a pretty important term. So we've looked at KL divergence. We're looking at VAEs, which measure a notion of divergence between distributions P and Q. This Jensen-Shannon divergence is just another way of measuring divergence between 2 distributions. And this Jensen-Shannon divergence is actually very closely related to KL divergence in the sense that it's the symmetric KL divergence. You're going to take a KL between P and the average of P and Q, and you're going to take the KL between Q and the average of P and Q, and you're going to take the average of both of those. So it's also a divergence measure between P and Q. And that basically means that, if you have a discriminator, what you're trying to get a generator to do is to minimize a divergence measure between data distribution and generator distribution. Essentially getting your model's generator distribution to match my data distribution as well as possible as measured by this Jensen-Shannon divergence. So there's a bunch of properties here. One interesting thing is, just as a thought exercise, why do we use the average of P and Q here? Right? Why can't we just say Jensen-Shannon divergence as KL between P and Q plus a KL between Q and P and take the average between those? And again, that relates to the fact that for KL, the support is super important. Right? Essentially, you take this term when you're doing KL, you'd be expectation over P log P over this. This term is on the denominator, so this has to be this cannot be 0 if P this cannot be 0 for regions where P is 0. Otherwise, you'll be dividing by 0. So essentially, the average distribution between P and Q is done such that the support covers both P and Q so that the KL divergence is well defined. And that essentially gives us the GAN training algorithm. You've seen this before when LP talked about it, but in general, you're going to sample some real images. You're going to sample some noise vectors. You're going to run these noise vectors through your generator to get some synthesized images. And you're going to essentially alternate the optimization of fixing the generator and optimizing the discriminator and vice versa. And you're going to optimize both of these parameters by gradient descent for the generator and gradient ascent for the discriminator. So the discriminator will try to best classify real images to be 1 and fake images to be 0. And the generator is going to optimize the opposite of that. It's going to try to fool the discriminator. And recently, we've seen a lot of improvements in GANs, most of which are essentially based on these loss functions. I think this was a very important paper that came out, which essentially looked at this vanilla GAN based on this Jensen-Shannon divergence and found a bunch of issues with it. So again, going back to this Jensen-Shannon divergence, I'm getting the figure back from KL here again. So for both, so Jensen-Shannon divergence essentially makes use of 2 KL divergences, right? And we know that for KL divergence, the support is really important, right? You don't want the support to be 0 in the denominator. And these, for many of these divergences, they're only defined on regions of Z, where both P of Z and Q of Z are non-zero. And you're going to measure the differences there. But the issue here is that if my data is in really high dimensional space and my data lies on some low dimensional manifolds, then just starting with Z and just relying on gradient-based methods to get Z to a region of high support for Q and P is really difficult. Right? The true data manifold and my generators, my generative models data manifold can have negligible intersection in practice. And at regions where they're negligible, the KL divergence are either undefined or infinite, or it can be even 0. So that makes it really hard to optimize for Jensen-Shannon divergence as a metric between 2 distributions, your data distribution and your model distribution. So what this paper did was to introduce a different type of notion of divergence. It's called the Wasserstrom objective. This Wasserstrom objective is a different type of divergence. It's also called the Earth mover's distance. Essentially what it means is that if I have a distribution looking like this and a distribution looking like this, how much mass has to be moved from this distribution to this? And mass is defined as the amount of mass times the distance which you have to move it from. So in this case, if this is 1 unit of mass and this is 1 unit of movement, then the Earth mover's distance here will be 1. So the good thing here is that it doesn't really care about the support. It's trying to move it across the support. If the support is far apart, that's just going to encourage into the loss. But it mostly compares in this direction, the amount of mass that you have to move to make one distribution into the other. And there's many good properties of Wasserstrom distance. I'm not going to go into all these details, but it's much more well defined, even on high dimensional in high dimensions, and where supports do not overlap. And it's also really easy to optimize. It has a dual form, which is really easy to implement in the GAN settings. And just to get a good visualization, so assume this is my density of my real images, a Gaussian here, and here's my density of fake images. Because their supports are not overlapping, the gradients that you get for regular GAN, your KL divergence is 0 almost everywhere. So you're going to get very small gradients, vanishing gradients that are of 0 value, which cannot push your density of real and fake together to actually get something informative. On the other hand, your Wasserstrom GANs actually remains to get really good linear gradients that gives you a good training signal to bring this towards here and your density of fake towards here. Yeah, I think I'm out of time, but I think that was most of it. Next Tuesday, I will go more into some GAN applications, and I'm also going to talk about some reinforcement learning applications. So just a quick roadmap. Today was mostly about GANs. I think GANs and VAEs for continuous space for images. And we'll soon realize that you're going to apply these VAEs and GANs to discrete space, such as that for generating text. You're going to get a bunch of issues. And that's where some techniques of reinforcement learning will come in, which is that allows you to compute these gradients of the discrete data much more easily. So next Tuesday, we're going to talk about reinforcement learning. And then on Thursday, we're also going to talk more about reinforcement learning and introduce this technique called policy gradients, which will allow us to revisit many of these generative models for discrete outputs, which need to be optimized using policy gradients. All right, thanks everyone.